Okay, so welcome back. We're on page 273 talking about this concept of the speed up versus the cost. So let's say you hired one guy to replace the roof in your house. And it's going to take this guy 5 days to replace the roof because he's only one guy. He's going to be going up the ladder. He's going to be, shoveling off the old stuff. He's going to be cleaning up the stuff on the ground. He's going to be lifting the roofing material up there and then hammering it in place. I mean, one guy, it's going to take 5 days to do. So you decided, well, I want it to go faster than that. So I'm going to hire 5 guys to do that. And it can be done in 1 hour a day, right? So you've sped up the process by having more people. You've also sped up the cost. Now, cost here could be kind of confusing. Let's say, for example, this is completely ridiculous hypothetical, but let's just say that it costs, I don't know, I'm making this stuff up. It costs $100 for one person a day, okay? But you only get $100 paid. So you get paid $100 doing your work at 7-Eleven. So you only have $100 in your wallet. So you could hire one guy because every day you get $100 and then you pay that guy $100, right? But if you haven't saved up anything, well, then you can't have 5 guys working because when they're done, they're all going to have their hand out wanting their money, and you're not going to have enough money to do that. Now, that sounds a little trivial, but let's just talk about it from an energy budget. Let's say that your power supply is only good for 600 watts, and so if I did this thing slowly, I won't bump over my budget. But if I did a bunch of them, hired a bunch of roofers and they all work together, then I could exceed the amount of power I got on my device. Okay? So yeah, that cost doesn't necessarily mean money, right? It could be other limiting factors. Okay, so typically the speed up factor, if I have 5 people, it's probably going to speed up by a factor of 5. But what happens is there a point of diminishing returns? If I had 10 people, would it go 10 times faster? Maybe. Okay, 100 people. If I did it 100 people, could it be done 100 times faster? No, right? I mean, there's a point where, they're just bumping into each other. Well, that's overhead that we're going to be talking about here in just a minute, where you have multiple tasks happening and there's just too much energy, so to speak, in setting things up and bumping into each other. I'm have to wait for you to step out of the way before I can do my thing, right? So it's not infinite. Okay. So the term scalability is the ability of an algorithm, typically, since, hey, that's what this is about, an algorithm to be easily converted to being a parallel kind of a thing. So parallel tasking, its ability to go to parallel tasking. So let's just say the simplest example of finding the largest number in an array or finding the smallest number in an array, right? Well, it's fairly obvious that if I had an array of 100 and it went through and hunting for the smallest one, it's going to have to look at them all, right? But if I broke that into 2 tasks, and this guy did 50 of them, this guy did 50 of them simultaneously, well, then I could probably get somewhere near twice as fast. Now, is it going to be exactly twice as fast? Or is there going to be just a tiny bit of overhead? Maybe 10% overhead, maybe? What do you think? Okay. All right. So, let's kind of sort of do one, rather than just to yap about it. So here we go. This is a modern way of doing multitasking, okay? This is not something that's in the textbook at all because they're talking philosophical. So let's just look at this thing for a minute. So what I've done here is I've got one where I'm have a method called find smallest. Okay, so I have an array of 100, and then I go through here, and I do it 10 times, and I give me a brand new set of random stuff. I start my stopwatch, find it, and then spit it out. Okay, nothing fancy here, right? Now, just to make this a little bit more interesting, what I've done here is I threw a 1 second sleep in here just to demonstrate that it takes a long time, because otherwise, this is such a trivial task. So I threw a sleep statement in there to deliberately slow it down. Okay, cool. Now, and then I do another one. So this is the the second version of smallest. So this was the smallest where I give it the starting and ending location. In other words, this one is 0 to 50, and then the other one is 50 to 100. Okay? Now, don't worry about the semantics of how this thing works, okay? This is just a C# way of creating an asynchronous task, okay? It fires up a task, and then you run the tasks, and then you wait for them to finish, and then you get the answers back. So in this particular case, I fire this guy up, does the first half of the array. This one fires up the second half, but they're going to be running simultaneously. I wait for them to finish, and then I get their results, and we're done. So I'm going to run this, and let's just see how well this thing works. Okay, first of all, it's fairly obvious that the second one ran one heck of a lot faster, didn't it? Is it exactly twice as fast? No. It's close. I mean, you got to admit, that's pretty good. 97 versus 171, that's pretty good. So there is a little bit of overhead. I mean, I could go in and like break it up into, to 4 tasks, and it would probably, the overhead would be a little bit more. And maybe if I broke it up into 8 tasks, the overhead would be to the point where it's not making any sense anymore. And maybe if I broke it up into 16 tasks, I probably wouldn't get any improvement whatsoever. Okay, so you see how this thing works? I take a simple task and I break it up into multiple CPUs, but there's kind of sort of got to be a sweet spot in there of, how do you do this? How many tasks do you put the thing in? Okay, so let's get back to the textbook now that we had a demonstration of this. So the PRAM model on page 274. This is, PRAM stands for the Parallel Random Access Machine. Okay, whatever. So what happens if 2 CPUs want to write to the same spot of memory, or two CPU cores want to write to the same spot in memory simultaneously? Now, I will tell you, in modern operating systems, contrary to what the textbook says, in modern operating system, that's really not capable of being happened. Each process has its own dedicated chunk of memory, and they do not normally overlap. If you want to write an application that deliberately shares memory, well, then you're going to have to pay attention to this. But normal, everyday application, and we're not talking about fancy CPUs and cores. That's not what we're talking about. I'm talking about a single process. Let's say you have a machine that has 1 CPU and 1 core, but you've got 4 processes going on, right? So one of them is, I've got Chrome, and I've got Visual Studio, and I've got all these things are running, right? But behind the scenes, they're not sharing any memory at all. Okay, so typical modern operating systems don't have this issue at all. So they're talking philosophically and in the scenario where you might want to deliberately write a program to share. Okay, so just having said that. So there's one of them in here. It's called concurrent read, concurrent write, which means I can read and write to any location without any issues at all. Okay, that's pretty weird. Concurrent read, exclusive write. Now that kind of sort of makes sense. In other words, multiple CPUs could read any spot, but only one of them can write to one location, because there's no contention if you're reading from a location, but there is contention if you're writing to a location. And then the ERCW, exclusive read, concurrent write, nah, that didn't make any sense. And then the EREW, exclusive read, exclusive write. So the CREW, which was the second one, concurrent read, exclusive write, that kind of sort of sounds kind of normal, doesn't it? And so the CREW model for how to read and write to shared memory is probably what makes sense for most applications that are written to do precisely that. So in modern applications, like I'm going to use C# as an example, if I want to make it share, there's a thing called a memory. Oh, by the way, there's lots of choices. Okay, I'm just picking on one. There's one called a memory mapped file. It makes it sound like because it has the word file in it, makes it sound like I'm opening a file. Not really. You're kind of sort of opening a file, but you're actually opening a chunk of memory. So I could have 2 operations, two processes, both talking to that file, which happens to be a chunk of memory, and then you could pass data back and forth, typically using the CREW model. Okay, so a memory map file is the technique in a modern scenario of how you could share data. Now, that's not the only technique. So next one we're talking about is the simple parallel operations on page 276. So they have some pseudocode in here, but they kind of cheat, okay? In the pseudocode in the book, they say parallel start and parallel end. Like, wow. Okay. Well, clearly those things do not exist anywhere in any programming language anywhere on the planet. That's just wave of the hand saying do stuff here that makes that happen. Okay. All right. So on page 277 and 278, they have this this thing where this is kind of sort of what I did, except they're doing it with shared memory. All right. So I'm going through and creating a parallel start, and I go to some number, and I read from memory, and then I write to memory, okay? If x is greater than y, this is supposed to be something that's going to be finding the maximum value in a list kind of a thing. So I write that to chunk of memory, otherwise I write x to the chunk of memory and then just keep going. That way, multiple one of these things each one of them could say, wait a minute, is this the current one? So when I'm writing to m, I get to write that, x goes to m or y goes to m, and so each one of them could look to see which one it is. Okay, is this real? No. But let me show you this guy. Ooh, the log of the count. Okay, now, they took the count divided by 2 and said log of count, is that's how many one of these parallels they wanted to do. So there is a rule of thumb. And the rule of thumb is, remember I told you, like, you can't have 100 people working on your roof at the same time. You'll just spend all your time bumping into each other. Plus, the example here, if I told it I wanted to do this in 16 different processes, 16 tasks all together, most likely I'm not going to get any benefit. Remember all that? There's a point of diminishing return. So the rule of thumb is that the log of I'm doing like 100. So log of 100, you know what the log of 100 is. You don't even have to look, right? If I round it off, remember the binary search guy? How many levels, right? It's 7, okay? So basically, you should use no more than 7 tasks, 7 parallel operations. That, by the way, that's no means a scientific way of doing it. I'm just saying that's a rule of thumb on how you kind of know, if I'm working on a list of 100, probably no more than 7 parallel processes. And to tell you the truth, it's probably, below that. 7 is when the break even, and I don't want to go to break even. I want to be something better than break even, right? Okay, which is why they cut it in half. But anyway, all right, here it goes. So, assuming that they have 2 CPUs, okay, fine. One CPU starts at the beginning and stops halfway. The other CPU starts at the halfway mark and stops at the end, just like my little application. So in theory, that cuts it in half, right? So if before, okay, now philosophically, I'm not necessarily talking about the practical application, but philosophically, if this would be an O sub n, wouldn't it? I mean, wouldn't you think that this algorithm by itself would be just a plain O sub n? Find the largest. That would definitely be, in my way of thinking, that would definitely be an O sub n. So find the largest using 2 CPUs. Well, that would probably be in like that, right? Find the largest using 4 CPUs. I'd probably still go like that, right? Find the largest using, 8 CPUs or whatever, right? It's all going to be the same. It's going to be linear. The more CPUs you put into it. Now, this is not without regard to the fact that you're going to bump into each other kind of a thing. So just from a big O notation, the number of cores you throw at it, the number of parallel operations, so it's divided by 2, divided by 4, divided by 8, or whatever. Okay, making sense? Well, good, because we're coming up on the 15-minute mark.